Hello everybody, welcome back to Controlling the BBT playlist. In this video we'll talk about observers. We'll explain what they are, why we use them, how we design them leveraging composed built-in function, and how we deploy them using Altair Activate. Though we will not go too much into details regarding the underneath mathematical theory. Hence, if you would like to deepen your knowledge about this topic, you'll find a related chapter in the System Dynamics and Controls ebook. Let's start. In the last video, we'll come up with an optimized PID controller with anti-wind up, and we have asked ourselves if it was possible to further improve our BBT system performances. So, let's see what can be improved. And let's focus on the derivative action of the PID controller. We see that we have numerically computed the derivative of the ball position, and this has a drawback. The high frequency noise gets amplified. So, to minimize this drawback, we have applied a low pass filter. But what happened is that in this way we are introducing some time delay, which worsens the system performances. It's clear that there is a trade-off between these 2 points. So, can we find a good balance between them? Actually, in this video we will not try to find a proper trade-off, but we will investigate an alternative and better solution, which is observers. The observer is a dynamical system designed to estimate the state of a system from measurements of the outputs. In few minutes this definition will become clearer. Its advantages are that it can be used to estimate states which are not measured directly by sensors, and it filters noise with almost no delay. At this point, it should be clear why our system performances can be improved using an observer. In this video, we will talk about linear observers, but in general also non-linear ones exist. As we have already stated in this playlist, the linear model of the plant in the state space representation can be used to design our observer. And to be all aligned with terminology, we will refer to the x-vector as the state or the internal state of a system, and to the y-vector as the measurement or external outputs. Of course, the linear model should produce results accurate enough compared to the real system. Indeed, we have seen that we are in this case with our BBT. Instead, if the linear model isn't accurate at all, the observer will produce poor estimates, and the system performances will decrease. Before designing our observer, we need to verify whether we can actually implement it on our system, which means that we need to check the observability of the system. The observability is a measure of how well internal state of a system can be inferred from the measurement of its external outputs. So, a system is said to be observable if the behavior of the entire system can be determined from the system output. It follows that if a system is observable, it is possible to reconstruct the system state from its output measurement using an observer. In Altair Compose, checking the observability is as simple as calling one built-in function, the one here reported, and we will see how to use it. Once we have checked our system is observable, we can design our observer. In our case, we are measuring the position of the ball in the x and y direction, and our observer should produce the estimates of the internal state, which is made up of both ball position and velocity, in the x and the y direction. Now that the goal is clear, let's tackle the mathematical formulation. As we have said, the starting point is the system state space representation. If we skip some mathematical steps, which are detailed in the ebook, we come up with the observer formulation. In this formulation, we find the same ABC matrix, but also a K matrix. When we talk about observer design, we mean that we need to determine this K matrix, which is known as the observer gain matrix. Here, we propose 2 ways to determine this matrix, leveraging 2 Altair composed built-in functions. The first function is called place. Since the observer is a dynamical system, it will be characterized by some poles. So, given the A and B matrix and the desired poles, the place function will return the K matrix. The observer poles should be placed farther on the left compared to the system poles, so that the internal state estimates converge faster to the actual internal state. Generally, the observer such design is called the Leuenberger observer. The second function is called RQR. In this case, the user does not have to provide as input the desired poles. In addition to the A and C matrices, he has to provide two weighting metrics, usually referred as Q and R matrices, which are used in a minimization problem solved by the RQR function. Also, in this case, the function returns the K matrix. Generally, the observer such design is called Kalman filter or observer. Again, further details regarding these functions and observer design can be found in the System Dynamics and Controls ebook. Once we have determined the K matrix, we can go back to the observer formulation, and we can easily rearrange it into a more convenient form, which is the state space representation. So now it should be clear why we have defined the observer as a dynamical system. The observer takes as input the same input of the system being observed, which is the U vector, but also the output measurements of the system being observed, which is the Y vector. And it returns as output the estimates of the internal state of the system being observed. The next step is to deploy the observer and combine it with our controller. So let's switch to block diagrams. This is the PID controller. For sake of simplicity, here we are not considering the end-to-end up scheme, but we will introduce it back in Altair Activate. The inputs of the controller are the reference and our measurements. Let's see how this block diagram gets changed by adding the observer. This time, the controller is receiving as inputs the references, both the velocity and the position one, and the internal state estimates produced by the observer. In particular, this kind of observer is called full state observer because we are using all its estimates in the controller. Actually, this is not the type of observer we are going to deploy. You can notice that we are using the estimate position even though we have available the measured position of the ball. Hence, in many cases, it is more robust and convenient to use a reduced order observer, which means that we actually use the observer only to estimate what we cannot measure, which in our case is the ball velocity. Now, let's make two final considerations. The first is that, of course, we are going to add the end-to-end up scheme. And the second one regards the derivative branch. If we set the reference velocity to 0, we should recognize that it looks really similar to the derivative branch of the PV controller. So let's recap what we have achieved so far. We have designed and optimized a PID controller with end-to-end up, which has great performances and eliminates the unwanted effect of integral wind up, magnified by saturations. Then we have added an observer, which prevents the numerical calculation of derivatives and it filters noise with almost no delay. And automatically, when combining the observer with the PID controller, we turned the derivative branch to look like the derivative branch of the PV controller, which is not affected by derivative kick. And now, let's verify these improvements on the real BBT using Altair Activate. If we look at the controller, we see the PID controller with end-to-end up. And we also see that we are providing the reference both for position and velocity. In this case, we are setting the reference position and the reference velocity to 0, which means that we want the ball to stay still at the center of the table. And now, let's see where and how we are deploying the observer. This is the observer, which gets as input the servo motor's rotations and the measured position of the ball, and provides as output the estimates of the system internal state. As mentioned, we are using a reduced order observer. Hence, we will only use the velocity estimates. The observer is designed in the Initialization tab. First of all, we check if the system is observable through the built-in function. Then, if the system is observable, we design the observer. Based on the value of this variable, which is defined at the beginning of the script, we design and deploy the Kalman filter or the Leuenberger observer. The Kalman filter is designed through the alqr function, defining the q and r weight matrices. Instead, the Leuenberger observer is designed with a built-in place function, specifying the poles. As previously said, the observer has to be faster than the system being observed. Hence, we are placing its poles farther on the left compared to the system poles. Now, let's understand what is sent back to the controller as input. We are sending back the measured position in x and y coordinate that we will use in the proportional and integral branches. And we are sending back the velocities in x and y coordinates for the derivative action. But which velocities? This depends on the value of this variable, which is defined in the initialization script. If its value is set to 0, then we are sending back the velocity computed as numerical derivative of the position. Hence, we are not using the observer. Instead, if we change its value to 1, we are sending back the estimate velocities provided by the observer. Before verifying the positive effect of the observer, let's start from the worst case. So far, we have always filtered the sensor output with a low-pass filter with a cutoff frequency of 100 radians per second. Let's see what happens if we remove this filter. So, we are not using the observer and we are not filtering the sensor output. The sensor signal is affected by noise. If we do not filter it, our system turns out to be really nervous, with the table shaking really fast to keep the ball still in the center. Now let's re-enable the filter and let's rerun it. There is a great improvement. The table doesn't shake that fast anymore, and also the motor's movements are smaller. And now let's see what happens when we deploy the observer. To do that, we use the execute block. This script sequentially launches 3 different simulations. In the first one, we are not using the observer. In the second one, the Kalman filter is deployed. And in the third one, the Leuenberger observer is deployed. Let's execute it. This is the first simulation without observer. This is the second simulation with the Kalman filter. And this is the third simulation with the Leuenberger observer. You might have appreciated that when deploying the observer, the Kalman or the Leuenberger one, the table looked less shaky. And from this plot, we can see that with the observer enabled, the motor movements are smaller. The Leuenberger observer seems to perform slightly better than the Kalman one. Now let's change the reference. We use a H-shaped curve So we want the ball to follow a trajectory, and we add a 2D animation of the BBT. The first time we do not use an observer. While the second time we use the Leuenberger observer. Also this time, you might have appreciated that when deploying the observer, the table looked less shaky. So, as we have seen and explained in this video, the adoption of the observer allows us to leverage even more our knowledge of the system. In our case, we have leveraged the linear model of the plant, which has proven being accurate enough. Once designed, the observer can be deployed for real-time applications, improving system performances, since it filters noise with almost no delay, and it provides internal state estimates that are used by the controller. Full-state observers can be deployed in case we are using cheap and noisy sensors, or if the system is placed in a really noisy environment. Instead, reduced-order observers can be deployed if we just need to retrieve those states that we cannot directly measure. For example, in our case, we have designed and deployed a reduced-order linear observer, which provides the velocity of the ball that we couldn't measure. Of course, everything comes for a price. In fact, there are some side effects. First of all, the observer is accurate only if the system model we are leveraging is accurate. Then, if some unknown disturbance continually perturbs the system away from where we think it is, the observer will produce really poor estimates, which eventually could lead also to instability. Finally, a more practical consideration. When deploying the observer on a PCB, we should consider that it might be more computationally expensive than accessing some sensor measurements. That's it for this video. If you would like to deepen your knowledge about system and dynamics and controls, we encourage you to visit this link. In the ebook, you will find some of the topics we covered today and many others. Moreover, feel free to share any question you might have about Compose and Activate in the model-based development forum. Thank you for watching and see you in the next video.